Hi, this is Alex from devstories.eu. Astropy, Python for Astronomy, episode 5 of 15. Pandas is amazing for flat data, but what happens when a single column in your dataset needs to hold a time series, a physical unit, and a spatial coordinate? Standard data frames break down. To solve this, you need Tabular Data Mastery, the QTable class. If you work in Python, you already know Pandas. Pandas assumes your data is flat, preferring one simple value per cell. In astronomy, data is rarely simple. A single observation might require strict units, a matrix of values, or a complex celestial coordinate. Astropy provides a custom tabular data structure specifically designed for this reality. You will notice Astropy has both a standard table class and a QTable class. People often confuse the two. The standard table tracks unit information as background metadata, but it returns plain NumPy arrays when you extract a column. A QTable enforces strict unit awareness. When you retrieve a column from a QTable, it guarantees you get a native Astropy quantity object back. The physical unit is permanently attached to the numbers. Let us walk through building a QTable. You start by importing QTable from the astropy.table module. You can construct it using a dictionary where keys are your column names and values are your data arrays. Suppose you are creating a simple catalog of galaxies. Your first column is plain text. You assign a list of strings representing the galaxy names. Now you need to record where these galaxies are. You do not want separate disconnected columns for right ascension and declination. Instead, you create an Astropy skycord object containing the positions for all your galaxies. You pass this single skycord object directly into your table as the second column. This is a Mixin column. Mixins allow complex Astropy types like skycord or time objects to act exactly like standard data arrays inside the table. You can slice, sort, and filter the table rows, and the Mixin object automatically keeps its internal data perfectly synchronized. Next, you need to store flux measurements across 3 different wavelength bands for each galaxy. In a typical data frame, you would be forced to create 3 separate columns. In a QTable, you use a multidimensional column. You define a single array with a shape of n rows and 3 columns, attach a physical flux unit to the whole thing, and assign it as your third table column. This is where it gets interesting. The QTable accepts the multidimensional array natively. A single row in that column now holds a fully contained array of 3 unit-aware measurements. When you print this table, Astropy formats it cleanly. It aligns the nested arrays and displays the units directly under the column headers. Your metadata and your measurements are locked together. The QTable is not just a spreadsheet. It's a specialized container built to respect the physics and geometry of your data. Thanks for hanging out. Hope you picked something new.